In previous videos, we studied the rule of sum and the rule of product, factorials, and also solved problems on these topics. Today we will learn the formulas for the number of arrangements and the number of combinations. So let's say we have a box with n balls numbered from 1 to n. We already know that the number of ways to order them is the factorial of n, that is n times n minus 1 times n minus 2 times and so on times 2 times 1. When ordering, we sequentially take balls out of the box, write down their numbers on a piece of paper in the order they appear, and leave these balls on the table, not returning them to the box. But what if we want to take out not all n balls, but some number k of them? Of course, the number k cannot be less than 0 and cannot be greater than n. Otherwise, the physical interpretation of the process breaks down. So, we will proceed in the same way as we did when deriving the factorial. We have k positions from 1 to k. How many balls can compete for the first position? Of course, we can choose any of the n balls for this. Next, we have chosen the ball that took the first position. How many balls can we choose for the second position? Of course, we have n-1 options for this. For the third position, we have n-2 options. For the fourth, n-3 and so on. For the kth position, we have n-k plus 1 options left. We must multiply all these numbers following the product rule. Excellent, this is the answer. We can leave it in this form, but it seems too cumbersome, doesn't it? Let's try to find a way to write this expression more compactly. Note that the factorial of n is equal to n times the factorial of n-1, that is n times n-1 times the factorial of n-2 and so on. Therefore, we can write the factorial of n is equal to n times n-1 times n-2 and so on times n minus k plus 1 times the factorial of n-k. Thus, we can write the answer as the factorial of a divided by the factorial of n-k. So, the definition. The number of arrangements of k elements from n, often called k-permutations, is the number of all possible ways to choose k elements from n distinct objects in a specific order. It's denoted as a of n and k. Let's compute some arrangements. A of 0 and 0 is equal to 0 factorial divided by 0 minus 0 factorial. It's equal to 0 factorial divided by 0 factorial, that is 1 divided by 1, that is 1. A of 1 and 0 is equal to 1 factorial divided by 1 minus 0 factorial, that is 1 factorial divided by 1 factorial, that is 1 divided by 1, that is 1. A of 1 and 1 is equal to 1 factorial divided by 1 minus 1 factorial, that is 1 factorial divided by 0 factorial, that is 1 divided by 1, that is 1. A of 2 and 0, that is 2 factorial divided by 2 minus 0 factorial, that is 2 factorial divided by 2 factorial, that is 2 divided by 2, that is 1. A of 2 and 1, that is 2 factorial divided by 2 minus 1 factorial, that is 2 factorial divided by 1 factorial, that is 2 divided by 1, that is 2. A of 2 and 2, that is 2 factorial divided by 2 minus 2 factorial, that is 2 factorial divided by 0 factorial, that is 2 divided by 1, that is 2. A of 3 and 0, that is 3 factorial divided by 3 minus 0 factorial, that is 3 factorial divided by 3 factorial, that is 6 divided by 6, that is 1. A of 3 and 1, that is 3 factorial divided by 3 minus 1 factorial, that is 3 factorial divided by 2 factorial, that is 6 divided by 2, that is 3. a of 3 and 2, that is 3 factorial divided by 3 minus 2 factorial, that is 3 factorial divided by 1 factorial, that is 6 divided by 1, that is 6. A of 3 and 3, that is 3 factorial divided by 3 minus 3 factorial, that is 3 factorial divided by 0 factorial, that is 6 divided by 1, that is 6. Let's note some patterns. First, for any n, a of n and 0 is equal to 1. Why is that? As we remember, the factor of 0 is equal to 1 because the only way to arrange nothing is to leave everything in its place. Similarly here, the only way to choose 0 objects from any number is to choose none of them. Second, a of n and n is equal to the factorial of n. What is the reason? Of course, the number of arrangements from n by n is the number of all possible ways to choose all the balls in some order, which is essentially the number of ways to order all n balls, and that is the meaning of the factorial of n. Third, a of n and n minus 1 is equal to a of n and n. This seems a bit strange. Why is that? Let's write it out. A of n and n is equal to the factorial of n divided by the factorial of n minus n, that is the factorial of n divided by the factorial of 0, that is the factorial of n divided by 1, that is the factorial of n. A of n and n minus 1 is equal to the factorial of n divided by the factorial of n minus n plus 1, that is the factorial of n divided by the factorial of 1, that is the factorial of n. Indeed, the formula is concise. How can we understand this on an intuitive level? The point is that when we choose all the balls except one, only one ball remains in the box. We get a product like a of n and n minus 1, that is n times n minus 1 times n minus 2 times and so on times 3 times 2. If after that we wanted to choose all the balls, the only one ball can compete for the last position, and our previous result would be multiplied by 1, that is, it would not change. Therefore, a of n and n minus 1 is always equal to a of n and n. Let's solve a couple of problems. Problem 1. How many ways are there to select a 100 meters plus 200 meters plus 300 meters plus 400 meters relay team from 30 people? Solution. We can select a runner for the 100 meters in 30 ways, 200 meters in 29 ways, 300 meters in 28 ways, and 400 meters in 27 ways. We get a of 30 and 4 is equal to 30 times 29 times 28 times 27, that is 657,720 ways. That's the answer. Problem 2. How many ways are there to select 4 people for 4 different positions if there are 9 candidates? Solution. Each a of 9 and 4 is equal to 9 times 8 times 7 times 6, that is 3024 ways. All our previous discussions focused on order, that is, on the sequence in which we draw balls from the box. That is, we took objects from some set of elements with no order and created a set of elements with an order such that, for example, the ordered pair 1, 2 isn't equal to the ordered pair 2, 1. But what if we now want to obtain a set of objects without a fixed order? That is, if before we obtained some ordered list, now we want to obtain some set. This number is called the number of combinations from n by k and is denoted as C of n and k. Let's say we have already selected k objects from n in some order. How many ways are there to rearrange the selected objects? Of course, the factorial of k. And if before we considered these options different, now we should consider them the same. Therefore, we obtain the formula. C of n and k is equal to a of n and k divided by the factorial of k, or C of n and k is equal to the factorial of n divided by the factor of k multiplied the factor of n minus k. Let's count the number of combinations for some parameters. C of 0 and 0 is equal to 0 factorial divided by 0 factorial multiplied by 0 minus 0 factorial. That is 0 factorial divided by 0 factorial, that is 1 divided by 1, that is 1. C of 1 and 0 is equal to 1 factorial divided by 0 factorial multiplied by 1 minus 0 factorial. That is 1 factorial divided by 1 factorial, that is 1 divided by 1, that is 1. C of 1 and 1 is equal to 1 factorial divided by 1 factorial multiplied by 0 factorial. That is 1 factorial divided by 0 factorial, that is 1 divided by 1, that is 1. C of 2 and 0 is equal to 2 factorial divided by 0 factorial multiplied by 2 minus 0 factorial, that is 2 factorial divided by 2 factorial, that is 2 divided by 2, that is 1. C of 2 and 1 is equal to 2 factorial divided by 1 factorial multiplied by 2 minus 1 factorial, that is 2 factorial divided by 1 factorial, that is 2 divided by 1, that is 2. C of 2 and 2 is equal to 2 factorial divided by 2 factorial multiplied by 2 minus 2 factorial, that is 2 factorial divided by 2 factorial multiplied by 0 factorial, that is 2 divided by 2, that is 1. C of 3 and 0 is equal to 3 factorial divided by 0 factorial multiplied by 3 minus 0 factorial, that is 3 factorial divided by 3 factorial multiplied by 0 factorial, that is 6 divided by 6, that is 1. C of 3 and 1 is equal to 3 factorial divided by 1 factorial multiplied by 3 minus 1 factorial, that is 3 factorial divided by 2 factorial multiplied by 1 factorial, that is 6 divided by 2, that is 3. C of 3 and 2 is equal to 3 factorial divided by 2 factorial multiplied by 3 minus 2 factorial, that is 3 factorial divided by 1 factorial multiplied by 2 factorial, that is 6 divided by 2, that is 3. C of 3 and 3 is equal to 3 factorial divided by 3 factorial multiplied by 3 minus 3 factorial, that is 3 factorial divided by 0 factorial multiplied by 3 factorial, that is 6 divided by 6, that is 1. Note some patterns. First, for any n, C of n and 0 is equal to 1. Indeed, to select 0 objects from any number of objects, there is only one way, to select nothing. Second, for any n, C of n and n is equal to 1. Indeed, there is only one way to select all objects from all objects. Third, for any n and k, C of n and k is equal to C of n and n minus k. At first glance, this symmetry seems surprising, but it's easily seen from the formulas. C of n and n minus k is equal to the factor of n divided by the factor of n minus k and the factor of n minus k. That is, the factor of n divided by the factor of n minus k and the factor of n minus n plus k. That is, the factor of n divided by the factor of n minus k and the factorial of k. That is, C of n and k. Why does this happen? Because whenever we select a set of k balls from a box of n balls, we automatically determine the set of n minus k balls that we left in the box. So it turns out that the number of ways to select k objects is the same as the number of ways to select n minus k objects. Let's solve problems about the number of combinations. Problem 3. Chess championship is held in one round, with 18 chess players participating. How many games will be played? Solution. To calculate the rating for one round, we need to compare each player with each other. This means that each of the 18 chess players must play against all the others. That's 17 games per player. But each game involves 2 players, so we get the answer. 18 multiplied by 17 divided by 2, that is 153 games. That's the answer. This is the number of combinations C of 18 and 2. That is the number of all possible unordered pairs of 18 elements. Problem 4. This problem once again shows the difference between arrangements and combinations. First, 10 distinct points are chosen on a line. How many segments are there with boundaries at these points? Second, 12 distinct points are chosen on a circle. How many arcs are there with boundaries at these points? Solution. First, a segment is uniquely determined by its boundary points and their order is unimportant. There are C of 10 and 2 is equal to 10 multiplied by 9 divided by 2, that is 45 ways to choose the boundary points. This is the answer to the first item. Second, an arc is determined by its boundary points, but in this case, their order is important. For example, suppose 2 points A and B are marked on a circle. Then we get 2 arcs, the first from A to B, the second from B to A. Thus, to choose an arc, there are A of 12 and 2, that is 12 multiplied by 11, that is 132 options. This is the answer to the second item. Task for mind. Suppose we have a box containing n blue and m red balls. All blue balls are numbered from 1 to n. All red balls are numbered from 1 to m. First, how many ways can we draw 5 balls in a fixed order? What if the order doesn't matter? Second, how many ways can we draw only 3 blue balls from a box if the order matters? What if the order doesn't? Third, how many ways can we draw only 2 red balls from a box if the order matters? What if the order doesn't? Fourth, how many ways can we draw 2 blue and 3 red balls from a box if the order matters? What if the order doesn't? We will cover this problem in the next video. Subscribe to stay up to date. We also need the following statement. Theorem 1. C of n plus 1 and k plus 1 is equal to C of n and k plus C of n and k plus 1. Proof. The first method, manually. C of n and k plus C of n and k plus 1 is equal to n factorial divided by k factorial and n minus k factorial plus n factorial divided by k plus 1 factorial and n minus k minus 1 factorial. That is, n factorial multiplied by k plus 1 plus n factorial multiplied by n minus k divided by k plus 1 factorial n minus k factorial. That is, n factorial multiplied by k plus 1 plus n minus k divided by k plus 1 factorial and n minus k factorial. That is, n plus 1 factorial divided by k plus 1 factorial and n plus 1 minus k plus 1 factorial. That is, C of n plus 1 and k plus 1. The second method, combinatorial. Let us be given a set M consisting of n plus 1 elements. The number C of n plus 1 and k plus 1 is the number of ways to select a subset of k plus 1 elements. Let us fix some element x of the set M. It may either be included in the desired subset or not. If X is included in the desired subset, then we have to select k elements from the remaining n elements. There are c of n and k ways to do this. If X is not included in the desired subset, then we need to select k plus 1 elements from the remaining n elements. There are c of n and k plus 1 options for this. Following the sum rule, we must add the resulting values. C of n plus 1 and k plus 1 is equal to c of n and k plus c of n and k plus 1. Remember this formula. If you enjoyed this video, please give it a like and subscribe to the channel so you don't miss the next ones. You can also support me with a one-time or regular donation on Patreon and donation alerts. This way, you'll help me create more useful educational content. See you next time. Math is life.